In this video, we'll continue our discussion of flux by working a couple examples. Again, of our radial vector field with the unit circle and our rotational vector field, just kind of to make sure the definition makes sense to us. All right, I see my definition up there. I see x primes and y primes. I need to figure that out, so I'm going to write r prime. They didn't give me what that is, but it's just a unit circle. We know that. That's cosine of t, sine of t. So it says I just need x prime and y prime, so I'm going to write that out. Xt equals cosine, y of t equals sine. And we can go ahead and find our x prime of t equals negative sine t. And y prime of t equals cosine of t. All right, remember we're going to do two different problems here. We have the vector field x, y, and that's x comma y. There we go. And that's my vector. I need to put this in terms of t, so I will do that. This is cosine of t, sine of t. This is my f and my g. I also have my x prime, y prime. So x prime of t is equal to negative sine. We already have this. I guess I don't need to rewrite that. So to find our flux, outward flux, it's going to be the integral from t equals 0. We didn't define this, but t goes from, in the unit circle, 0 to 2 pi. All right, and then we do, our definition says to take f and times it by y prime. So f times y prime is going to give me cosine squared t. And then I'm going to minus, and then it's going to be g times x prime, which is a positive sine squared t dt. This gets me, all right, the integral from 0 to 2 pi of 1 dt, which is just going to be 2 pi. Well, this makes sense in this case for the radial vector field. I mean, a radial vector field just spits things out at an orthogonal. Each one's met at, or a 90-degree angle at each point. So it makes sense that we get 2 pi. That's a whole circle. There's crosswind all the way through. It makes sense that we get this measurement. Now, looking at B, let's go ahead and predict if it is a rotational field and it's only pushing in the direction of the tangent vector, there should be 0 flux. But let's go ahead and calculate that. So for this function, xy, this vector field, our vector was, is it negative y? Yeah, negative y, x. I need to put these in terms of t. So it's going to be negative sine t, comma cosine t. And then we're having to, this is f and this is g. So the flux goes from t equals 0 to 2 pi again. And we want f times x prime. That's our definition at the very top. F times, or is it y prime? Y prime, be very careful. We get negative sine t cosine t. And then minus, and then it's going to be g. So it's cosine times x prime, which is going to be a negative sine t cosine t dt. And you can see that this is going to be 0. The integrand is 0, integral over 0, 0. This makes sense in our rotational field because the vector field is just pushing along the tangent lines, tangent vectors of my rotation, causing there to be 0 flux. There's no crosswind, while the flux in this one is a constant all the way across.